Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk. All right, today is September 9th, 2021. We have Stefano Longari from the Politecnico Institute in Milan, Italy, where he is a Ph.D. student and researcher. He's going to be talking today about CAN error handling, vulnerabilities, and attacks. Stefano, thank you for being with us today. The stage is yours.
Hello and welcome to this ASRG webinar in which we're going to discuss about CAN error handling attacks and countermeasures, and specifically how some vulnerabilities implemented in the CAN protocol itself enable attackers to take control of the vehicle and how. Specifically today we're going to discuss about two known attack techniques and countermeasures that we have designed in the last few years to detect those kind of attacks. Now, first of all, thanks to everyone in the acknowledgements. I am Stefano Longari, and without the help of the people mentioned there, we wouldn't have been able to conclude our research. First of all, as I mentioned, I am Stefano Longari. I have obtained a Ph.D. at Politecnico di Milano in the last 2 months, and I'm currently working there as a postdoc. My research has focused throughout my whole Ph.D. on automotive security and specifically on automotive intrusion detection, either based on machine learning or based on specific techniques. Now, if we want to discuss about CAN error handling attacks, we definitely first need to discuss about what CAN is. Well, CAN, or Controller Area Network, is the current de facto standard in the automotive world for onboard networks, which means that CAN is used to make ECUs, or electronic control units, which are the computers and boards inside the vehicle, communicate with each other. And although in the next few years we will see the advent of automotive Ethernet, at the moment CAN is the definitely most common network present in the world. So it's probable that every single vehicle currently on the road has at least one CAN network in it. And the reason being that it was designed to be functional for automotive environments. In fact, CAN has been developed by Bosch in the 1980s exactly with the goal of being useful for automotive environment. And you will see in the next few slides how this makes sense, as long as you don't consider external communication being part of the equation. In fact, as I mentioned, CAN is the current de facto standard, and it's based on the data link and physical layers of the ISO-OSI model, which means that basically its goal is that of explaining to ECUs how to represent physically the message. So how do you write a 1, a 0, how do you write the information, and how do you define a packet, and who is the sender and the receiver of the packet. Actually, in CAN, this is not exactly how it works, but we can see it in this way for now. Now, CAN was developed with the focus on safety, since vehicles are things that are moving fast on the road. In the 1980s, Bosch had the goal of be sure that the messages being passed by in CAN were reliable. And this was done by creating a network that doesn't really have many issues with electromagnetic interferences. It has a broadcast nature, which makes it faster to communicate from point A to point C, because you don't need to pass from point B. You just have one single network on which everyone is listening to. And the way arbitration is designed in CAN favors the most important messages. We will see how this works. This basically implements some kind of real time while being extremely cheap. In fact, the important thing on the other side was that Bosch needed some extremely cheap protocol, since the number of CAN networks inside a vehicle are not small, and having direct connections, for example with Ethernet, at the time was definitely too expensive, both in terms of actual raw materials, both in terms of, for example, weight that was added to the vehicle. Just to clarify, CAN is a multi-master protocol with broadcast nature and with a bus topology. Really briefly, this means that in CAN only one node is a master at a single time, but basically everyone can become a master if they manage to win arbitration and they manage to start sending a message. Broadcast and bus topology are kind of straightforward. I assume that they are known concepts, and the idea is that basically everyone reads everything that is passing, and that everyone reads everything that anyone else is sending on the bus. As you can see here, the message on CAN is sent as a differential voltage between two different cables called CAN-H and CAN-L, which are divided by a 120 ohm resistor. Now, as I just mentioned, the physical layer is a differential signaling over two wires. The data link layer instead, here I want to focus on how the arbitration is done, because it's extremely important for our case today. And the arbitration is done over CSMABA, which means carrier sense multiple access bitwise arbitration. This is what enables real time in CAN, or let's call it some sort of real time. It's technically not real time. Now, from the start, the idea is that when we send a message on CAN, we send either a 0 volt or a 5 volt differential over the two cables CAN-H and CAN-L. As you can see, the logical 0 is represented by a 5 volt differential, and the logical 1 is represented by a 0 volt differential. Here you can see what we read instead of what we are actually sending. Now, the dominant bit is the 0, the dominant voltage is the 5 volts basically, and the recessive bit is the 1. Why am I saying this? Because basically what happens on the bus is that if two different nodes are sending a 0 and a 1 at the same time, the 1 completely disappears, because the 5 volt differential overrides it. And why is this important? Because this is how arbitration is done in CAN. What does this mean? It means that, assuming that we have three different nodes that want to send a message at the same time, they will all start their message. We will see this later in more details, but they will all start their data packet with some given bits, and then with their ID, the frame identifier. The ID basically represents the sender of a message. Now let's assume here that node 1, node 2, and node 3 want to talk at the same time. They will start with a bus idle message and then the start of frame all together, and then they will start their ID. You can see that node 1 sends a 0, while node 2 sends a 1 and node 3 sends a 0. Now all nodes will read what they see on the bus while writing, and the reason being that node 1 will send a 0 and will read a 0. Node 3 will send a 0 and will read a 0 on the bus, but node 2 will send a 1 on the bus, but as we mentioned before, since the 1 is recessive, he will read the 0 from node 1 and node 3 and not the 1 it sent. This will mean that node 2 lost arbitration. It will stop sending their message right now, considering that there's someone with a higher priority that is sending a message at the bus at the same time. We can go on the same way. Node 3 sends a 1, node 1 sends a 1, then node 1 sends a 1, but node 3 sends a 0, which means that node 1 loses arbitration here, and node 3 is able to finish its ID. If a node finishes its ID on the bus without reading anything wrong, it will consider that it won arbitration and will then start sending the rest of the message. Okay, we're not going to discuss too much about CAN data frames due to the fact that they're not the data inside the frame is not the focus of CAN error handling attack, but we still need to understand how they're implemented. A reason being that they are still the focus on every kind of attack, basically because they are the majority, they're 99.9% of the packets passing on the bus are data frames. Now, the idea in general is that, as we mentioned before, the ID is the first thing that arrives, and it's either an 11-bit ID or a 29-bit ID. In the case of 29, it's peculiar that it's not exactly a 29-bit ID, but it's two parts of an ID, so in a way that enables the first section of the packet to be exactly identical to the 11-bit one. And then we have some part of packets, we will discuss them in a second, but also the important thing is we have 8 bytes of data, or 64 in case of CAN-FD. What I want to care about here is, as you can see here from Wikipedia, we have the list of elements and fields inside packet. As you can see here, we have the ID, some information. But what I want to focus about is that there's some fields that are fixed and they must be in some kind of way. So for example, we focus on the CRC delimiter here, which must be recessive. This is going to be important in the future, and we will understand why in the next few slides. Now, the other things that I want to focus on here are the rules that are not enforced, but that should be implemented on CAN. In fact, each ECU owns a set of IDs, which means that an ID should only be used by one specific ECU. Say, for example, ID 70 is used by the engine ECU. Then no one else should use that ID to send any kind of information. And the reason is that, first of all, data are defined as part of an ID, which means that I know that in, for example, a packet with ID 70, I will find information arriving from the engine ECU. So if someone else uses it, I don't know exactly what's inside it. But most of all, if this other ECU wanted to start talking at the same time as the engine ECU, since arbitration is done on the ID, what would happen is that they would collide, since both would send completely their ID at the same time without seeing each other, because they would see, as we can see here, they would see them sending exactly everything identical without recognizing that someone else is talking on top of them. So each ECU owns their set of IDs and no one else should use them. Just be mindful about this. No one checks this. It's just a formal thing that should be implemented in every kind of network. The second important thing I just already anticipated is that a field of each ID has a fixed meaning, which means that in ID 70, we will always find the same kind of information. Say, for example, the engine is sending the RPM of the vehicle in that ID. In the first and second byte of that ID, we find the engine RPM represented as an integer. Then every time we see ID 70, we will find that information there. Now, what happens after is that in this way, if I'm another ECU that is interested in knowing what the RPM of the vehicle is, I will know in advance by design that ID 70 has that information inside, and I will wait and listen on the bus searching for ID 70 to recover that information. Last but not least, the majority of packets in CAN are periodic, and this is extremely important for some kind of attacks. We will not focus on those exactly right now, so I won't enter into much into the details, but it's important to know this because we need to understand how the traffic is done. And generally speaking, the vast majority of packets and of information that are passing on the bus are periodic, which means that, for example, again, the engine ECU will send ID 70 10 times a second with the current RPM of the vehicle. or something like this. Generally speaking, the frequencies go between 100th to 1 second to 5 seconds or something like that, depending on how constant, how important it is to have a fast update of the information. So aside data frames, we're going to discuss about error frames, which are the only ones that we care about. Error frames in CAN are extremely simple, and they are composed only of 6 consecutive identical bits, either 6 zeros or 6 ones. The reason for 6 zeros or 6 ones to be considerable as an error flag is that on CAN we have bit stuffing is implemented, and bit stuffing is a technique that ensures that every X bits, and in our case every 5 consecutive identical bits, we will add one of the opposite kind. Reason being that since CAN is not clocked, this helps in understanding and counting correctly. So it avoids, for example, situations in which you would have 64 zeros in the payload of a data frame, and that would mean that we would have a 5-volt differential for the bit time of 64 bits without having an actual clock, which may happen that we would then count 63 or 65 on the receiver side. So what we do is with just every 5 identical bits, we add one of the opposite kind. This bit obviously is removed by the receiver before interpreting the packet. So just to say that after saying this, the point is, so if we send 6 consecutive bits, we're basically making an error. And this is why the error flag is composed in this way, because it ensures that the receiver will read the message as an error itself and therefore trigger the error handling protocol. So what happens when a message is being sent in this way? So what happens, for example, if during a data frame I see an error flag, is I will just stop considering that message as valid. So I will not try to interpret that message, I will just discard it and wait for it again. Reasons for error frames usually are on the sender side. If I wanted to send a 1, for example, and instead sent a 0, I will send an error frame on the data frame, basically with the idea of saying, hey, I made an error, please do not listen to this message, I will send it again. On the receiver side, generally this comes from some lack of compliancy from something that I read on the bus. So for example, some sender that sent something that was not compliant, and I will send an error on the bus saying, hey, you made an error. Now I want to make a brief intermission to then focus on the security side of CAN and understand what are the issues from a security point of view, discussing about how much CAN is a key to automotive attack. And the answer obviously is it definitely is one of the most common elements that all attacks have in common. If we study the majority of known attacks and known proof of concepts designed in the state of the art against, for example, Teslas, but also the Jeep hack, the known Jeep hack from 2015 from Miller and Balasek, well, in all these cases, CAN was heavily part of the attack. And the reason is that CAN is not authenticated, and the rules that I mentioned before, for example, about having only one ECU sending one ID, are not actually enforced by anything. So it's extremely easy for an attacker to just behave as if it was a different ECU. So for example, the engine ECU or the brake ECU, and ask another ECU to activate the brakes or to activate the ABS or to accelerate or to activate, for example, the cruise control and lane assist and so on. All these kind of things have been proven possible and are generally implemented through a CAN. There are 2 works from Miller and Balasek that are extremely interesting from this point of view. And most of all, one from 2016, where they actually analyze how advanced attacks against CAN are implementable. And they show that basically it's almost always possible to convince an ECU to act on our request if we know how to formulate that question. So CAN is definitely a key to automotive attacks, but I want you to understand why. I want to briefly discuss on what happens here. So generally, again, this is our CAN bus with different ECUs connected to it. We have a keyless ignition module in this case, an engine control unit control module, and a body control module. The attacker is somehow connected to the bus. I don't want to discuss exactly now how this is possible. It can be done either from remote or from by attaching something to the actual bus, for example, through the OBD2 port, depending on how the OBD2 port is shielded from the bus. But nonetheless, so we have different ECUs connected to this bus. And at this point, since CAN is broadcasted and authenticated, what I can do is always injecting frames. So say that keyless ignition module should be the one that checks whether my wireless key is the correct key, and then sends to the engine control module an information saying, okay, you can turn on the engine because I authenticated this key. Then me as an attacker should always, or it's most commonly, be able to send the same frame that the keyless ignition module would send to the engine control module, turning the vehicle on. Right? So generally speaking, this is possible. There are some kind of countermeasures that are being implemented in the last few years, most commonly intrusion detection systems, but often we don't really have those intrusion detection systems, we don't really have authentication, and therefore we're able to create those kind of messages, to forge this kind of messages and ask the vehicle basically to do whatever we want, which is what Miller and Balasek did in 2015, proving that they were able to actually control the vehicle from remote. Now, can we detect these attacks though? So assuming that we implement intrusion detection systems in this context, can we actually implement an intrusion detection system that is able to detect these attacks? Well, more than one company already designed those, and the answer, generally speaking, is yes. How do automotive intrusion detection systems work? Because we need to understand how they work to understand what they're capable of detecting. Generally speaking, obviously the specific implementation is an industrial secret, so we're not going to discuss about the actual implementation, but we can see from an academic point of view, what are the techniques that are most commonly designed and implemented. Now, the most common one, and actually probably I would say the most effective one, is a frequency-based module, which means that since CAN messages, as we mentioned before, are usually periodic, we can check the frequency at which these messages arrive and use that frequency to understand whether there has been an attack because there's more messages than there should be, or there's less messages than there should be. The second type of intrusion detection system is a specification-based one, which means that we have a knowledge of how a message should be designed, should be built, and we can check that the actual messages that are passing on the bus do not break some kind of rules. So for example, say the speed should go from 0 to 200 and it's currently minus 50. So we can check some kind of rules of that kind, and we can do this also in a dynamic way, potentially, knowing which are the physical boundaries, for example, of some rules. So for example, the speed of the vehicle wouldn't be able to go from 0 to 100 in 1.5 seconds. So either the increase is gradual or we're not going to accept it. Finally, there are machine learning based intrusion detection systems. Now this is obviously more of a academic side, an academic point of view on the element of intrusion detection systems, because we don't really have any machine learning based IDS currently on road, or at least being designed to be built to being inserted on vehicles, but we do see the strength of machine learning for some kind of intrusion detection on vehicles. We're not going to enter into the detail of machine learning based intrusion detection systems though. Now, regarding frequency and specification based, the question is, can we evade them? So what are the chances of evading them, and what can we do to avoid being detected? Well, there's actually a couple of methods that we can implement. For specification-based intrusion detection systems, the only thing that we need to do is comply with rules. So we can't create packets that completely go against either physics or against the format of how the packet should be designed. So for example, again, taking the example from before, ID 70, which should have the RPMs of the vehicle in the first 2 bytes of the payload. If there we put something different, so for example we put the representation of whether the brakes are activated or not on the 4 wheels, then obviously we will have a different format, and this will not be accepted. But if we comply with the specification, we should be good. At the same time, frequency based, we should comply with the frequency. This is not as obvious as the first one, because how do you comply with the frequency if the frequency is occupied, if the period is occupied by the actual ECU sending the message? So say that we have a frequency of 10 packets in a second. The ECU that is sending the packet is already sending 10 packets in a second. So if we add even just 1 packet on top of them, we are going to break the frequency rules. So how do we solve this? Well, basically, if we are able to substitute or manipulate a real frame, we are complying with all the requests of intrusion detection systems. If we're able to maintain a specification that is acceptable, if we manipulate or substitute a real frame, we are basically complying also with the frequency, which means that we are going to be able to conclude our attack without being detected. Now, it's easier said than done though, because substituting a real frame or manipulating it is not obvious, obviously. Generally speaking, imagine this is our context as before. We have our keyless ignition module, the engine control module, and a body control module, and we want the keyless ignition module to send an information to the engine saying, okay, you can turn on. Well, what happens here? We need to understand what happens to understand exactly what can we do as an attacker. We have the microcontroller, which is going to create the frame. The microcontroller only creates the data, the payload, and knows the ID. So he decides, okay, I want to send on frame 20 this payload, this frame payload. It sends the information to the CAN controller, which is going to create the actual CAN packet as explained in the specification of the data frame. So it's going to create all the packet, and it's also going to add the bit stuffing part. And finally, the transceiver is generally only used to receive the bits to be sent and transform them it basically transforms them in CAN compliant electrical signals. What I want to focus here on is only that the CAN controller is the one that handles errors. What does this mean? It means that if we receive an error frame on top of a data frame, the CAN controller is not even going to send the information to the microcontroller. The CAN controller is only going to just discard all the data payload and the packet itself and just wait for another one. When the CAN controller receives a complete and valid data frame, it is going to relay the information to the microcontroller, not before. Now, how do we solve this? I already mentioned this, so I'm not going to lose time on it, but remember arbitration, because arbitration implies that if we want to send a 1 and a 0, the 0 will override the 1. This is done for the arbitration, but it is always true on CAN. So even while the packet is passing, I can write a 0 on top of a 1, and it will always overwrite the 1. The reason for this not happening in the while without an attack is that if I lose arbitration, I lose the right to talk on the bus from a theoretical point of view. So me, ECU that wants to be compliant, will not ride on the bus in that moment. But if I want to, as an attacker, I will always be able to write a 0 and overwrite a 1. In fact, this is something that we can abuse. CAN error handling is based on this information, and if I override the 1 with a 0, I'm going to send the sender is going to send an error frame. What I want to say before entering into the details of the attack is how fault confinement works though. So basically we mentioned error handling and the fact that if I see a 0 when I wanted to see a 1, I will send an error frame on top of my message to invalidate my data message, because I want to say basically, hey, I made an error, please do not consider my current message. Now, on top of this, since CAN is designed to stand on a vehicle that is going to be in the wild for the majority of the time and is not going to be often maintained, the ECUs are not going to be modified or controlled often, I want to be sure that if an ECU fails and start not reading messages correctly or not sending messages correctly, the ECU should stop talking on the bus, because I would like the ECU that is failing to not bother all the network in order to let everybody else continue with their work. Now, to do so, CAN implements a fault confinement technique. And how does this work? So in general, an ECU is in a status that is called error active status. And in this status, an ECU is able to send error active flags. And error active flags are error flags that are composed of 6 zeros. What does this mean? Basically, it means that the ECU that is in error active mode can override a wrong message of another ECU with 6 zeros. If an ECU makes too much errors, both while sending messages or while reading them, it is going to increase the counter, and when this counter reaches 127, the ECU is going to pass into a mode that is called error passive mode. Error passive mode lets the ECU do whatever it wants anyway, but it's not going to be able to send error active flags, it's only going to be able to send error passive flags. And what this means is that the error flags are going to be composed of 6 ones, and therefore if this ECU that is in error passive mode sees an error in another ECU, in another ECU's message, it is going to send 6 ones, but 6 ones are going to be overwritten by the actual message of the initial ECU. And therefore, in error passive mode, I am not able to stop other ECUs from making errors. I'm only able to stop myself from making errors by sending error passive flags. Now, I don't really care about the error passive mode. What I really care is the bus off mode. In fact, when an ECU makes so many errors that the counter of it's called transmit error counter or receiving error counter goes over 255, the ECU shut itself off the bus. This in bus off state, in bus off mode, the ECU is not able to send messages on the bus, and this is going to remain like this up to either the ECU is reset or up to when the ECU detects 11 sequential ones on the bus. In that case, the ECU goes back to error active mode, considering that it basically is now able to read whatever it wants because it's not making errors. Now, this is the fault confinement technique, as I mentioned before, has been designed on CAN with the goal of stopping an ECU that is starting to fail. The problem is that this process is abusable by attackers to shut other ECUs off the bus. In fact, an attacker ECU can convince the target ECU to kick itself off the network by staying on the network, reading what's passing, and every time the ECU that I want to shut down sends a message, I know when the ECU sends a message because the IDs related to an ECU should only be sent by that ECU, so I'm sure that if, for example, in this case we said the keyless ignition module owns ID number 20, every time I see ID number 20 on the bus, I'm sure that it's the keyless ignition module that is sending it. So what I can do as an attacker is, while the payload, for example, or another part of the message with ID 20 is being sent, I can write a 0 on top of a 1 of that payload, and I'm sure that the ECU itself will consider that it made an error because it will read a 0 while sending a 1, and it will send an error frame. Sending the error frame, it will increase its error counter, and eventually, if I repeat this enough times, I am going as an attacker to kick the ECU off the network. In fact, by sending the 0 on top of the 1, I am first of all going to delete the packet, because the ECU that is sending the packet itself will see the 0, say, okay, I made an error. It will send the error frame, and this will mean for everybody else that the previous packet is not to be considered. On top of this, I can actually make a set of steps to set the ECU to bring the ECU that I want to kick off the network in bus off state. And when the ECU is in bus off state, the ECU is not able to speak. So which are these steps? Well, the first one obviously is to know the IDs that the victim uses. So for example, in our cases is ID number 20 for the keyless ignition module. This can be done by reverse engineering the CAN IDs or by owning DBC files that the manufacturer usually have secret though. But in general, like there's multiple ways for me as an attacker to discover which IDs are being sent by an ECU. Once I know which IDs I'm searching for, I am going to wait up to when I see those IDs passing on the bus, and I will just do that by reading bit by bit the first part of the packets, searching for the arbitration field. Now that I know that the current packet being sent is a packet being sent by the ECU that I want to shut down, I will wait for a 1 in that packet, and I can do this in two different ways. Either I can react to a 1 being sent, so I can just, for example, wait for the data field and search for a 1 being sent in the data field and switch it to a 0, or I can wait for the CRC delimiter. As we mentioned at the beginning, the CRC delimiter is a bit that is designed to be a 1 by design in the packet. So I'm always going to be sure that when we arrive to the CRC field and then we arrive to the CRC delimiter, the CRC delimiter will always be a 1. So I can be ready when the last bit of the CRC is being sent and know that if I send the 0 after that bit, I am going to overwrite a 1 with a 0. Again, I can write the 0 on top of the 1, and this will trigger the error, but the error is interestingly going to be, as I mentioned before, generated by the victim, not by me. I am going to send the 0 on top of the 1, and the victim himself will send the error frame, saying, okay, I made an error, me, the victim, have made an error because I sent the 0, but I wanted to send a 1, so please do not acknowledge my message. Now, just to clarify, an error like this on the bus will increase the transmit error counter of the victim ECU of 8. So if I do this process 32 times, what happens is that I get to 256, and I'm sure that I'm going to send the ECU bus off. So once we know how to implement the attack, once we have this idea of how to implement the attack, we wanted to implement it. And we did this in two ways. First, we created a mock CAN bus with an Arduino Uno, which was representing the actual attacker with a CAN transceiver, and we tested whether it was actually feasible and whether it was actually something that would have stopped an ECU or any other CAN device from speaking. Once we realized that this was actually feasible, we wanted to implement it in a real-world scenario, and we did so on an Alpha Giulietta. In fact, in the Alpha Giulietta, we can see this is the layout of the CAN networks inside the Alpha Giulietta. The OBD2 port is connected to the CAN B line, which has the parking sensor module, which was our target in order to not endanger ourselves with any other information. Everything on this bus is being sent at the same time, just to clarify. So the instrument and pilot cluster module will definitely send some information on the bus. The airway control module may send some information on the bus. The audio control module will send some information on the bus, and so on, right? So we don't want to shut down the whole bus, because shutting down the whole bus will mean obvious detection, but also like incapability of using the vehicle itself. What we want to do is specifically target one ECU. In our case, is the parking sensor module. So we discovered what the idea of the parking sensor module was, and through the OBD2 port, we wanted to attack it. So just to clarify what the parking sensor module does, it sends different information depending on how close we are from an obstacle. And we all know, like by experience, that the vehicle usually beeps at different frequencies to tell us that we are too close to an obstacle. Well, what we want to do is completely remove this packet from existence. So as you have seen in the video, what happens is that the ECU is perfectly functioning. The park assist ECU is perfectly functioning up to when we insert our device in the OBD2 port, which is the yellow port on the right. At that moment, our device implements the attack and shuts the park assist ECU off the network, of the CAN network. And what happens is that you can see on the screen that the park assist becomes unavailable. Now, obviously, this is an example on a relatively non-safety critical ECU, but we can do the same process on any other ECU. Now, just to clarify, there are two similar techniques that can obtain this a similar result in different ways. One is from Cho et al. From 2016, and it's basically based on sending correct packets with the same ID of the victim, with the goal of sending the victim off the network by colliding on the data field of the packet. And the other is called Canon, and it has been published this year at the Security and Privacy Symposium, and basically bases itself on stopping the clock of the CAN transceiver in order to keep a zero loaded, let's call it, while sending a message, to then wait for the message of another ECU and release the clock in order to finish sending said zero, and therefore overwriting a message of another ECU. Both those techniques have the advantage against ours that they do not require an external device, which is definitely limiting. But at the same time, they are significantly harder to implement and not always implementable due to the constraint of having an ECU inside the vehicle itself that can do what they need to do. Now, this said, I'm not going to discuss that too much. What I want to discuss is whether this is preventable or not. So sadly, since it's based on protocol specification, these techniques, these attacks are not actually preventable, since they abuse of something that is intrinsic of CAN, which is that we can overwrite a 1 with a 0. It is also extremely hard to retrieve the logs to distinguish between an attack and a failure, because, as we mentioned before, the microcontroller doesn't even know of a message if the message is being overwritten by an error flag, because the CAN transceiver and the CAN controller will just discard it without even sending it to the microcontroller. Now, what are the possible attack scenarios that are implementable through these techniques, through the techniques we just presented to shut an ECU off the network? Where on the long run, one of the most common one may become that of ransomwares. An ECU, for example, could be connected to a device, could be connected to the vehicle that does not let the engine control unit receive the information by the key ignition system that it should turn on. And by doing something as simple as this process, the attacker can completely shut the vehicle down and then, for example, ask the driver to pay to have the vehicle released. Now, this is a future possibility. Currently, this is still not implementable due to the complications of having the screen that is connected to another ECU ask the driver to do something, and at the same time, due to the fact that it would be difficult to scale for an attacker, such attack, and therefore would not be particularly economically interesting. Now, as we mentioned before, though, the reason to implement an attack like this could be that one of avoiding detection from intrusion detection systems. In fact, if we shut down an ECU at a certain point, we can start sending messages on behalf of that ECU and no one will detect it. Reason being that no ECU will receive the information of the victim ECU being shut down, because there is nothing visible on the bus, if not just an ECU that is failing, that failed the message, which is acceptable usually. And then it just starts to send messages again. But after that moment, it's not the actual ECU sending the message, it's us on behalf of the ECU. Being a bus protocol and a broadcast protocol, it's hard, if not usually impossible, to detect which ECU is actually sending a message by analyzing the electric signals. This is actually something that has been studied. It's relatively possible to do, but extremely expensive, and it would require ad hoc hardware, which is not into the economic possibilities of car manufacturers usually. Different question is, if we cannot prevent it, can we detect the denial of service? Well, yes and no, as in, we can read the data from the bus by having a device that is reading bit by bit and not just by having a device that receives information only from the CAN controller, so something that is able to see and read CAN errors. The problem is we cannot really define whether an attacker is shutting an ECU down or if the ECU failed, as long as the attacker doesn't send messages after it. So, considering the two examples before, we shouldn't be able to detect a ransomware attack, but we would be able to detect an attack in which the attacker stops the ECU and then starts sending other messages. And why are we able to do this? So basically the idea is that we can define when an ECU is bus off. If we're able to understand when an ECU is bus off, then we know that if a message being sent by that ECU passes on the bus, but the ECU should be bus off, that message is not being sent by the ECU, but by the attacker. And this is what we're going to implement. How do we do this? We do this by studying how the CAN specification works on the transmitter receiving error counters and how they increase, how they decrease. How can we detect those counters increasing and decreasing by reading messages passing on the bus? So we need to understand how the transmit error counters of different ECUs work. Just to clarify, what we're going to do is we have our hypothetical attacker on the bus, and we're going to create a device, as we mentioned, that is able to read bit by bit. We want to count alongside any ECU what is their error status in order to understand if they are going bus off, right? So how do we do this? We understand exactly how the transmit error counter is increased in each of the ECUs. And to understand how the transmit error counter is increased from the outside, we need to understand what we can see on the bus when an error happens. So this is the list of rules, as we mentioned, that modify the error counters, and specifically we want to focus on those that modify the transmit error counter, because that's the only one that can kick the ECU in bus off state. So the first rule is, when the transmitter sends an error flag, its transmit error counter is increased. Easy to detect. Every time we see a message on a bus, we can consider the transmitter being sending an error flag. And why are we sure that the transmitter sends an error flag? for one of two reasons, because either the transmitter was sending the message, saw an error that he made, and then sent the transmit error flag, or the transmitter was sending a message on the bus, someone detects a message from the transmitter, that someone sends a 0 as an active error flag, and as soon as the transmitter sees a 0 that he wasn't sending, then the transmitter will react by creating an error itself and consider that it made an error on writing something on the bus. So the transmitter will eventually send a transmit error every single time an error flag appears on the bus. So we're sure that every time we see an error flag on the bus, the transmitter increases its error counter by 8. This doesn't happen in one of two cases. The first one is basically saying this exception basically means if there's no one else aside me on the bus, I am not going to consider myself making an error if no one acknowledges me. And the second one is just saying we don't consider an error in the arbitration phase if it's a staff error, but generally speaking, in arbitration phase we do not consider errors, which is easy. Now in these two cases we are not considering the transmit error counter increasing, which is not a problem. For up to now, we are able to detect each one of these situations and distinguish between them and be sure to count correctly the transmit error counter. Rule 4 says if a transmitter detects a bit error while sending an active error flag or an overload flag, the transmit error counter is increased by 8. What does this mean? This means if the transmitter is sending 6 ones, but instead, is sending 6 zeros, but instead it reads a 1, then I'm going to increase my counter of 8 again. Now, to clarify, this is not visible from the outside. The only one that can detect this is the ECU itself that is making the error. The good element of this, the good point of this, is that an attacker cannot exploit in any way this information to increase the counter without us being able to read it, because the attacker cannot trigger this event. Rule number 6, I'm going to discuss this by itself in the next couple of slides. Number 7 says after the successful transmission of a message, the transmit error count is decreased by 1 unless it was already 0. Basically, we're saying super easy. If we see a message going from start to finish, the ECU that has that ID should lower its counter of 1. Finally, a node is bus off when its transmit error counter is greater or equal to 256. Again, easy, we are counting correctly up to now. So we're going to discuss this in a second, but we're counting correctly up to now. So when we get to 256 or more, we're just going to consider an ECU off the network. And finally, rule number 12 explains us how to go back from bus off mode to normal mode, which is again feasible to read, because it says a node which is bus off is permitted to become error active, so no longer bus off, with its error counters both set to 0 after 128 occurrences of 11 consecutive recessive bits. When does this happen? We can find 11 consecutive recessive bits only and only between one message and another. So basically we are saying after an ECU is able to read 128 different messages on the bus and see them passing, then I am going to consider the ECU can go back to error active mode, because enough time has passed and we will try again to let the ECU work. Why is this useful? This is useful because we know that even if the attacker sends a victim bus off, after this time the ECU will come back online anyway. So after this time we have to consider that the ECU is not bus off anymore, and if it starts talking again, this is not the attacker talking, it's actually the ECU talking. So really briefly about rule 6. I'm going to discuss about rule 6 because if we don't handle this correctly, an attacker would be able of exploiting our detection to let us count incorrectly the number of errors made by an ECU and number of transmit error counters increased by a victim ECU. So really briefly, any node tolerates up to 7 consecutive dominant bits after sending an active error flag, passive error flag, or overload flag. What does this mean? It means that, as I mentioned before, when anybody sends an active error flag on the bus, everybody else will not read that flag as an error flag, but it will consider it as an error because it's not complying with a bit stuffing rule. So the reason for which active error flags are smart in CAN is that they intrinsically create an error that everybody else considers. But what happens in this case is that everybody else will then send an active error flag again, saying, hey, I found an error. So generally speaking, every time we see an active error flag on the bus, we usually see 2 active error flags on the bus, because we have the first one, and as soon as the first one finishes, the second one starts, which is composed of everybody else, as you can see here, saying, hey, I made an error. So after detecting the 14th consecutive dominant bit, in case of an active error flag or an overload flag, or after detecting the 8th consecutive dominant bit following a passive error flag, and here is the reason is that in this second case the first 6 bits were 1s, and then we have zeros, and after each sequence of additional 8 consecutive dominant bits, every transmitter increases its transmit error count by 8, and every receiver increases its receive error count by 8. So what we're saying is, if we have a first error flag here, and then our second error flag here, we give one, after these two flags, if we see other zeros, and specifically after each 8 zeros, we're going to increase our error counter of 8. This is done to avoid ECUs locking themselves in a sequential active error flag situation in which everyone raises an error after someone else raised an error. Now the problem here is that due to rule 6, we could have a same identical situation on the bus, so this situation here on the bus, which could be caused by different actual situations, like different events. Say for example, in this case, case 1, we have a victim and an attacker. The attacker finds the victim sending a 0, a 1, then another 1, and as soon as the attacker sees this 1, it starts sending zeros. If the attacker does this, we will see this event on the bus, right? And we can decide that obviously the first error we will count is here when we see the first error flag, but then we need to know after how many 8 bits, blocks of 8 bits, we want to start counting again. So we have our first error flag here, then the second error flag up to the 14th bit here, and here we increase again our transmit error counter of the victim, and so on and so forth. So after other 8 bits, we're going to increase it of other 8s and so on. This would be the first situation. The attacker though could do something different. The attacker could find a victim that sends 5 different zeros consecutively, and then a 1, and overwrite that 1. Now, the victim, in this case, will consider the first error flag being this one, and the second error flag being this one. So the victim will start increasing its error counter here, further away from the first one. So we have this delta here of time in which we don't know how long it took for the victim to increase its error counter again due to rule 6. Problem is, we cannot really do this. We cannot really never understand how this behavior is actually implemented. So what exactly happened in this specific case? And we have to choose and always consider as if case 1, so this case happened. And the reason for this is that if we always consider case 1, there are going to be situations in which the attacker still didn't finish its attack, and we already consider that the ECU, the victim ECU was bus off, and this is obviously negative for us. but we will basically always detect the attack. There's no way for the attacker to dodge our detection, to avoid our detection. In the second case, in case number 2, if the attacker knows that we are handling situations like this, he can always trigger situations like case 1 and stop here, like stop sending zeros here, and the victim is going to have increased its stack by 8 more, by 8 due to rule 6, while we are not still counting those 8 from rule 6. And in this way, the ECU should be, the attacker would be able to send the ECU off the network before we realize it. So we always have to choose to detect case 1, even if it's not what it. Now that we have explained all the elements that we are going to consider, this is the final result. This is our actual intrusion detection system represented as a finite state machine. Basically what we're doing is reading the packets that are passing on the bus bit by bit, trying to understand when an error flag is triggered, and then counting alongside the ECUs on how many times the error counter increases for each message. When the message ends without errors, we're going to decrease the error counter. When the rule 6 is triggered, we're going to increase it again multiple times if needed. And in this way, basically, we are always going to be sure that we are following every single ECU on the bus, understanding when its transmit error counter is being increased, and when the ECU goes actually bus off. If the ECU goes actually bus off, and we see again here its ID passing on the bus, we can raise a flag saying, hey, this is not the ECU that is talking, this is an attacker speaking on behalf of an ECU that he shut off the network. Again, this is the overall situation, the overall steps. First, we define which ECUs to defend, then we monitor the bus. Just to clarify, we need to monitor the bus from the beginning of communication because we need to be sure that we are monitoring the bus since all the error counters are at 0. Because if we start counting while ECUs have already some errors in the error counters, then we're not going to be able to realize when the ECU goes bus off. We count alongside each ECU that we want to defend from, and we detect when the ECU goes bus off. Up to this point, we still don't know whether an attack has been implemented. But if the ECU writes on the bus again, so once we know the ECU should be bus off, but we see an ID of the ECU passing on the bus, we're sure that this is not the ECU speaking, but it's actually an attack. And at this point, we can react. Just to clarify, this is our publication. Now, there are a couple of things that we could do to react to this event. And these reactions are of different kinds. The problem is that at the moment, we don't really have many solutions that are at the same time safe and meaningful. In fact, on one side, we can, for example, one of the most common hypotheses of what do we do when we detect an attack on CAN is we could switch to a safe or degraded driving mode, right? So maybe alert the driver and limit the use of electronics in handling the driving. This is actually feasible. The problem here is that if there's too many false positives, generally here the issue is if there's too many false positives, this event happens too often, and then it becomes annoying for the driver because it happens even when attacks are not actually being implemented. So this is something that is feasible up to the moment where we have a 0% false positive rate. In our context, our solution actually never showed the possibility of having false positives, so this could be a solution to implement, a reaction to implement in our context. The second type of reaction that we can implement is that of preventing attacks in the future. So we can just log everything that's happening to avoid other people being able to implement the attack. This is the currently most common solution for automotive attacks in general. Aside this kind of attack, but in general, all the intrusion detection systems on CAN at the moment usually behave like this. They only log the attacks and send the attack to a backend somewhere where someone analyzes it to understand how was it possible that the attack was implemented, in order to, say, for example, patch the software that led to the vulnerability and so on. Final solution is to attack the attacker. And this is actually only feasible with our solution that requires a modified device, a specific device that needs to be able to read each bit and to write on the bus at the same time. In fact, we could theoretically attack the attacker and shut the attacker off the bus as soon as we realize that the attacker is talking on behalf of the ECU. Is this meaningful? Well, this may prevent the attacker to actually obtain dangerous solutions and dangerous attacks on the bus after the victim ECU has been sent bus off. So it would definitely be a possible solution. Obviously, it leads to safety issues, and therefore to actually attack the attacker, we should be 100% sure that we're not going to shut down an ECU that is not malicious before attacking it and shutting it off the network. As a last point, we actually implemented our attack and our countermeasure on a testbed. And actually we did this both with an Arduino Uno as Copycan, which is the name of our intrusion detection system, and both with a high-end automotive AURIX board in order to understand whether there were limitations in using a simple microcontroller or a more complex one. And in both cases, what we implemented was a testbed in which Copycan, or our intrusion detection system, was reading on the bus, and there was an attacker. And then we had two different devices, one that was the victim / protected ECU that was trying to speak with some specific IDs, and then there was a traffic generator. And the reason for the traffic generator to exist is that we wanted to have as many valid collisions on the bus during arbitration or during other contexts, in order to generate as many errors as possible that were not generated by the attacker. So errors that would happen in the wild, in a normal environment, in a real CAN bus. And the reason was that we wanted to detect Rule 4 and Rule 6. So as we mentioned before, Rule 4 and Rule 6 are the two rules that we're not 100% sure to be able to detect. In fact, Rule 4 is not detectable, and Rule 6, as we mentioned before, we have to fall in one of two cases. But again, we created this testbed with the idea of detecting Rule 4 and Rule 6 in the wild, and we have never fell in situations in which the intrusion detection system failed. In fact, we have done the test multiple times, sending more than 10,000 frames per test, and the intrusion detection system always reacted exactly at the first message sent by the attacker on behalf of the protected ECU. So we're pretty sure that the intrusion detection system implementation works. So in conclusions, denial of service for CAN is not preventable, as in it is intrinsic for how CAN is designed that we can send zeros on top of ones and block the ones from passing. So if an attacker has the only goal of shutting an entire network down, he doesn't even have to implement complex attacks as the one that we just presented. He can just send continuous zeros and no one will be able to speak. But instead, an attacker that creates a targeted denial of service attack abusing of the CAN error handling protocol usually has a subsequent goal, which is that of, for example, speaking on behalf of the ECU that has been shut down. And in that case, the final goal of the attacker can be detected. So thank you very much if you've listened up to now, and thank you very much on behalf of ASRG for participating to those webinars. If you have any questions for me, please feel free to contact me through one of my contacts, and have a nice day.